Hello students, welcome to All Force e-learning channel. This is K. Nageshwara, your physics faculty. Today we are about to deal with session number 100. And in this session we'll discuss about few other applications of potentiometer. In the previous session we have already discussed about two applications. One is comparing EMFs of two cells. The other one is finding internal resistance of a given cell. When two EMFs were compared, what was the expression that we have derived? E1 by E2 is equal to L1 by L2. When the internal resistance was found, what was the equation we had with us? Small r is equal to what? L1 by L2 minus 1 into capital R. So that was the equation we have derived yesterday. And today we'll proceed ahead with a few other applications. Okay, so let us continue. So let us start with this application. The application is what? Comparison of resistances. So what I'm going to do is I'm going to take two resistances and I will compare those two resistances. Yesterday I told you what do you mean by comparison. Comparison in the sense, if you are having two resistances R1, R2, if you are having two EMFs E1, E2, if you say that E1 is twice E2, it means what you are doing, you are comparing, isn't it? So here also we are going to derive a relation for R1 by R2, how much will derive that. Okay, so that's what comparison of resistance in this sense. And that is something we can do with the potentiometer. Remember students, potentiometer, whenever you remember this, whenever you recollect this instrument, potentiometer, immediately you should recollect one very important point connected with this potentiometer. What is that? It is a device which is useful to measure absolute potential differences. The only reason for the capability of this potentiometer to measure absolute potential difference is it doesn't draw any current from the circuit. Okay, if at all, if potentiometer is connected, for example, across a resistance R1 or R2, okay, some resistance across some resistance, this potentiometer is connected. If since potentiometer is a self-driven circuit in the sense it will have its own cell. Okay, so it doesn't depend upon the circuit to which it is connected. Okay, so because of that reason, whatever potential value it gives, it will be very accurate. Instead of potentiometer, whatever voltmeter usually we use to measure the potential differences across the circuital elements, if you connect voltmeter, what voltmeter does, it's not a self-driven body. It draws current from the circuit. Because of that, whatever reading it shows, that will have some error in it. Okay, so potentiometer is something that can be used to find out the accurate value of potential difference across any circuital element. And the other use is you have already seen yesterday, comparison of EMFs of two cells, finding internal resistance, and today we will be dealing with comparison of resistances, and I will also deal with calibration of instruments like ammeter and voltmeter. Calibration in the sense correcting, or if any error is there in the instrument, identifying that error, rectifying that error is nothing but a calibration. Okay, so let us go ahead with this one, comparison of resistances. Here I have taken two resistances R1 and R2. This is how the circuit is arranged. Here this RH1 is rheostat. Rheostat is something whose resistance can be tuned, whose resistance can be changed. This, wherever you see this arrow mark, across a circuital element, that arrow mark indicates that this particular circuital element can be tuned. This particular circuital element can be changed. For example, if you are having a capacitor, something like this, and if there is a line across the capacitor like this, there is an arrow across the capacitors like that. That arrow mark indicates that you are dealing with a variable capacitor. If you are having a battery and if you are having a arrow passing through the battery, it indicates variable potential difference can be supplied by the battery. So variable resistance can be we can have it here. So if at all, if I wanted to change the resistance in this primary circuit of potentiometer, I can do that. I can change with the help of this rheostat. Let us say this AB wire is potentiometer wire. Okay. And this E, R, what is this? In primary circuit, in potentiometer, whatever cell we arrange, that cell's EMF is E, internal resistance of that cell is R, and here I have arranged one key. Okay, and this AB will have some resistance. Usually that resistance is denoted with capital R. Already we have seen that. Okay, and look at this secondary circuit. Okay, here two resistances were taken, and here also one variable resistor was connected. See, it's always suggestible to have variable resistors so that you can have a lot of freedom while dealing with the experimental setup. You can change what a current value, you can change. You can play with the circuit. You can change the resistance to whatever desired value you wanted to go. You can go with the help of rheostat. So here one rheostat is also taken. Here one key arrangement is there, here one cell is taken in the secondary circuit. Now look at this, forget about all these things. Our interest is, I wanted to compare R1 and R2. R1, I want to compare R1 with R2. So here, three, three terminals are taken, X, Y, Z. For example, if X and Y both are joined together, X and Y both are joined like this. What does it mean? It means this R1 is taken into the circuit, like now it's a part of this potentiometer arrangement. Okay, so this R2 is not connected to the potentiometer. If at all, if you make a contact between Y and Z, what does it mean? R1 and R2 both are taken into the circuit. Both are taken into the circuit. So since you have made initially, if we make a contact between X and Y, it means we are connecting potentiometer across R1 alone. We are connecting potentiometer across R1 alone. Okay. So let us say this potentiometer is connected across R1. For what purpose? I wanted to find out the potential difference across this one. What I can do? I can keep on tapping the potentiometer wire AB with the help of jockey. This is what jockey is. Jockey. Okay. So what I will be doing? I will be tapping here. If there is a deflection, I will tap here. If there is still deflection, I will tap here. Let us say somewhere here when it was tapped, the galvanometer is showing null deflection. Null deflection. Null deflection in the sense it is pointing 0. Galvanometer is pointing 0. What does it mean? It means there is no any current through this one. There is no any current through this part of the circuit. What does it mean? It means potential difference across this R1 is exactly equal to potential difference across this length. Let us say this length is L1. How much is that length? L1. I will take that length as L1. So whatever potential difference is there across L1, if that is exactly equal to potential difference across R1, then galvanometer shows null deflection. Or if galvanometer shows null deflection, how you have to understand that? It means potential difference across this resistance R1 is exactly equal to potential difference across this part of the length L1. Okay. So how to find out potential difference across this L1? Let X be potential gradient. Potential gradient. I want you to remember all the details connected to the potential gradient. Potential gradient X is equal to I into R by L. That I is equal to E by small r plus Rs plus R whole into R by L. These details are very important. Potential gradient is potential per unit length. Potential per unit length, if it is X, what will be the potential across length L1? X into L1, isn't it? Therefore, potential across a length L1 is equal to X into L1. Okay. Where L1 is what? Balancing length. Where L1 is balancing length. Balancing length is that is the length for which the galvanometer is showing null deflection. Okay. So according to our discussion, what was our conclusion? Whatever potential difference is there across R1, that is exactly equal to potential difference across L1. Therefore, potential difference across R1. Let us say there is a current equal to I passing through this circuit. Therefore, how it can be written? I into R1. Isn't it? I into R1. Now, these two potentials are equal, isn't it? Therefore, I R1 is equal to X L1. Let us take it as equation number 1. Let us take it as equation number 1. Now, what I am going to do is, I am going to remove this contact. I am going to disconnect this X from Y. Now, try to understand this picture, children. This part of the circuit is not connected to potentiometer, or potentiometer is not connected to this secondary circuit. Now, what I am going to do is, I am going to make a contact between Y and Z. What does it mean? It means this potentiometer is connected across this combination of resistances R1 and R2, series combination. In series combination, what will be the effective resistance? R1 plus R2. So, if you find a balancing length somewhere here, let us say for this R1 plus R2, somewhere here you have found the balancing length. Okay, let that balancing length be L2. How much is that balancing length? L2. What does it mean? It means potential difference across this combination of resistance is exactly equal to potential difference across a length equal to L2. How much is the potential difference across a length equal to L2? XL2, where X is potential gradient, isn't it? So therefore, if Y and Z are connected, and balancing length is equal to L2, therefore I into what is the potential difference across R1 and R2 together? Total effective resistance here is R1 plus R2. How much current is passing through them? I. So according to Ohm's law, potential difference across R1 plus R2 will be I into R1 plus R2, which is equal to X into balancing length L2. Let us take it as equation number 2. Now divide equation 2 with 1. What you will get? II gets cancelled. You will have R1 plus R2 by R1, which is equal to what? XX gets cancelled, which is equal to L2 by L1. So R1 gets cancelled. You will have 1 plus R2 by R1, which is equal to L2 by L1. Therefore, R2 by R1 is equal to L2 minus L1 by L1. So this is how you can compare two resistances. Okay, so this one is taken to the RHS side, L2 minus L1 by L1. Okay, so let us look at the other use of other application of potentiometer. It's about calibration. Listen to me, children. Calibration in the sense identifying error. If any error is there in ammeter or voltmeter, we have to identify. Without identifying that error, if I keep on using the same ammeter or voltmeter in the experimental setup, I will be always getting wrong values, isn't it? If ammeter is always showing, let us say, some error, if it is reading 2.1 amps, for example, ammeter, but the actual reading is 2 amps only. Okay, so how much is the error? 0.1 error. If at all, if I know that ammeter shows error equal to 0.1, what I will be doing? From the ammeter, whatever reading I will be getting, from that reading I will subtract 0.1 and I will be able to write down the accurate reading. Isn't it? So it's suggestible always when you deal with the experimental setup involving ammeter and voltmeter, you have to identify how much error is involved in those instruments. Okay, so let us see how this error can be identified with the help of potentiometer. And this whole procedure of identifying error is nothing but calibration. Remember, students. So let us proceed with the calibration part. Now let us discuss about calibration of ammeter and voltmeter with the help of potentiometer. Okay, I told you what calibration means. Calibration is what? Identifying the error in the instrument and rectifying that. This entire procedure is called as calibration. So let us have a look at this one, calibration of ammeter. So this is our primary circuit, potentiometer circuit, and this is entire part is secondary circuit, isn't it? So here, when cell is connected, I need it. You will know why we have to connect one cell here. And here I have taken resistance whose resistance value is equal to 1 ohm. Okay, intentionally it was taken like that. You will come to know why we have to consider 1 ohm resistance. Listen to me. If you are supposed to find out potential drop across 1 ohm resistor, what you will be doing? Using Ohm's law, V is equal to I into R, isn't it? If current passing through this resistance is known to you, let us say it is I. What is the resistance value here? 1. So V is equal to I into R. R replaced with 1. So you will have I into 1 I. So V is equal to I. I am not saying that potential is equal to current. I am saying that the value of numerical value of current is equal to potential. Okay, so that's where I am having advantage. Okay, so we'll go with the mathematical treatment. And similarly, voltmeter is also taken. So let us have a look at this one. What I'm going to do is, I'm going to connect this cell, whatever cell I have taken here, whose EMF is E0, I will take that into circuit. I will connect a potentiometer across the electrodes of this cell, so that what I will be getting? I will be getting a balancing length somewhere, somewhere I will get balancing length, and whatever potential drop is there across that balancing length, that is exactly equal to EMF of this cell. That's what my conclusion is going to be. Okay, so let us proceed. Let me tell you again, students, what I am trying to do. I am trying to identify error in the ammeter. How much current is shown by this ammeter? I value. It is showing that the current passing through this circuit is equal to I, but we don't know whether it is accurate or not. Okay, with the help of potentiometer, we will be able to identify the accurate value of current passing through this resistance. Okay, so if that value is known to us, and if that value is different from whatever value it is showing, how much it is showing? I. Okay, so if there is any difference, that's what we call it as error, and accordingly we can collect the data from the experimental setup. If excess value it is showing excess value, we can subtract. If it is showing lesser value than the actual value, then we'll add error. So like that, we can handle the error. This entire procedure is called as calibration of ammeter. So first what I'm going to do is I'm going to make a contact between this terminal 1 and 2. Okay, like this. Let us say 1 and 2 both are joined. It means this cell is, across this cell, this potentiometer setup is connected. Isn't it? Let balancing length is equal to, let us say, L0. How much is the balancing length? L0. What does it indicate? That implies EMF of the cell is exactly equal to potential drop across length L0. How much is the potential drop across length L0? X into L0. This X is what? Potential gradient. We have been talking about this potential gradient. So X is potential gradient. And here I don't know how much is that potential gradient. So what I can write, that implies potential gradient X is equal to E0 by L0. Let us preserve this equation for later usage. Now what I'm going to do is I'm going to disconnect this cell from the circuit, and I will connect this terminal 2 and 3 like this. These two are joined. 1 and 2 are disconnected, these 2 terminals are disconnected, and 2 and 3 terminals are connected. What does it mean? Now this potentiometer is connected across the resistance 1 ohm. Across the resistance 1 ohm. So whatever potential drop now I am going to identify across this resistance, I will take that potential drop as V. And that is equal to, let us say, balancing length corresponding to this one, somewhere here it is obtained. Let us assume like that. This is the jockey position. Let us say this is the balancing length. I'll take it as L1. Then potential drop across this one corresponding to this balancing length will be how much? X into L1. X into L1. That's how we will be writing. X into L1. Isn't it? And this V can also be written as potential drop across this resistance. Can also be written as, let us say, current passing through this one is actual current. I am talking about the actual current passing through this one is some I1. What is the actual current passing through this one? I1. If I1 is the actual current passing through that one, multiplied with the resistance. Resistance is how much? 1 ohm. What do we get? Current multiplied with resistance. Potential drop across this resistance. Isn't it? How much is that? I1. Okay, students. Let me tell you again, whatever I is shown in the circuit, that is the ammeter reading, and we don't know whether it is right or wrong. Now what we have done with the help of potentiometer, we were able to identify how much potential drop is there across this resistance, and that potential drop is equal to V. That V is equal to, eventually it has come out to be as I1. And what is this I1? The actual current passing through the resistance. Simple. Now I will take the difference between these two. That's what the error is. So this is the current shown by the ammeter. This is the actual current passing through the resistance. So what I can do, therefore, error delta I is equal to current shown by the ammeter minus the actual current. Current shown by the ammeter, I will take it as I only, minus this I1 can be replaced with XL1, right? XL1. This is equal to, how it can be modified. We know what X is. X is equal to what? E0 by L0. I minus E0 by L0 into L1. Therefore, error in the current is equal to I minus E0 by L0 into L1. So that's how you can identify the error. Once the error is known to us, we can access the data accurately from the experiment. Okay, if at all, if the actual current is 2 amperes, okay, let us say the ammeter is showing a 2.1. Let us say if the actual current is 3 amperes, let us say ammeter is showing 3.1. It means there is an error equal to 0.1. So what I will be doing, I will be subtracting 0.1 from all the current data that I will be looking in this ammeter. Okay, so that's how this ammeter can be calibrated. Okay, now let us try to identify calibration of voltmeter. The picture is quite similar to this one, except voltmeter is connected. Students, Ammeter is something which is used for measuring current, and this is always connected in series with the experimental circuitry elements. Okay, whereas voltmeter is something which is used for measuring potential difference. Since it is meant for measuring potential difference, it will be always connected parallel to the circuitry element. Remember this point, like this. Voltmeter is not meant for connected in series combination. Okay, it will be connected in parallel combination. And here, unlike in the previous case, here I have taken the resistance box. Again, resistance box is something where you can tune resistance within certain limits. You can tune the resistance. Okay, so just to have freedom of choosing appropriate resistance, whatever resistance I wanted to choose, I can choose with the help of resistance box, so that this resistance box is arranged. Otherwise, you can arrange any other resistance, simple resistor can be taken and it can be placed here, no problem. Okay, so here resistance box is taken. So my intention is what? I wanted to identify error shown by the voltmeter. And what is the reading here? It is showing V. How much is the reading shown by the voltmeter? V. And I don't know whether it is right or wrong. So what I will be doing, I will be taking this potentiometer into account, and I'll identify the error, and then I can rectify the data. Whatever error is there in the data, I can remove that. So here also the same procedure will be followed. First, the terminal 1 and 2 are joined. So if balancing length is L1, so this E0 is written as X into L1 or L0. Let us say balancing length corresponding to this E0 EMF is L0. So E0 can be written as X into L0, like in this case. Okay, so that implies X is equal to E0 by L0, isn't it? Now what I'm going to do is I'm going to disconnect this terminal 1 from 2, and I'll join 2 and 3. So what does it mean? It means potentiometer, now it is connected across this resistance box. Okay, so therefore let the balancing length is L1. If balancing length is L1, whatever potential is there across this resistance box, that potential, I'll take it as V1, is equal to what? X into balancing length is L1. Of course, I am not representing all those things. I want you to understand. So L0 is balancing length corresponding to E0, and L1 is balancing length corresponding to potential difference across this resistance box. So if this is the case, this X can be replaced with what? E0 by L0 into L1. So this is what? This is the actual potential difference across the resistance box. And what is this V? V is potential difference shown by the voltmeter. Okay, so this is the true value, this is the value shown by the potentiometer. Therefore, what is the error? The error delta V can be written as V minus V1, isn't it? So V, I'll keep it as it is. V1 can be replaced with this one, E0 by L0 into L1. So that's how you can find out the error in the voltmeter. Okay, this error can be positive, negative, 0. Definitely there will be some error, because potentiometer is the only gadget, only device that can identify potential difference across any circuitry element accurately. If you connect any voltmeter, definitely it draws some current from the main circuit. So whatever value it shows, definitely it will have some error. Okay, so here the error can be positive or negative. Okay, positive or negative. So that's how you can calibrate these devices, ammeter and voltmeter. Okay, so now let us proceed ahead with a few conclusions connected with the potentiometer. So now let us conclude this potentiometer part. I'll conclude with this one, sensitivity of potentiometer. Students, sensitivity, this word, it needs very deep inside all the time. When you talk about sensitivity of ammeter, when you talk about sensitivity of voltmeter, you have to understand this word very, very clearly. Okay, that's very much required. Sensibility, for human beings, what does it mean? Sensibility in the sense, so even for small things also we react or we feel very sensible. So few of you might be very sensible for even small issues also. So that's something like literally you can describe. But what about sensitivity corresponding to the instruments? Sensitivity corresponding to the instruments, you can define like this: how sensibly the instrument can respond. How sensibly the instrument can respond in the sense, in case of potentiometer, let me tell you, potentiometer, I have been telling you, it is something that can measure the potential difference accurately across any circuit element, isn't it? If it was able to measure even a very small value of potential difference, then I can say that it is more sensible. I can say that ammeter is more sensible if it can measure small values of currents also. I can say that a voltmeter is more sensible if it can measure a small value of potential difference. I can say that a galvanometer is more sensible if it shows large deflection for even a small value of current. Usually, galvanometers, sometimes it happens because of less sensitivity of the galvanometer. Though there is some current passing through the galvanometer, it doesn't show any deflection. But what is galvanometer? What do we know about galvanometer? If it shows any deflection, it means there is a current passing through the circuit. That's what our conclusion will be, isn't it? What if current is passing, small amount of current, and galvanometer is not showing deflection? It means it is having less sensibility. Okay, so the galvanometer's sensitivity is less. Okay, so I hope you have got an idea what sensitivity means. Let us talk about sensitivity of potentiometer. For example, I'll take potentiometer wire. I'm in the primary circuit. Let us say I am not taking rest of the elements in the primary circuit, resistance cell and all. This is the potentiometer wire. Okay, potential gradient X. How do we write this? Potential per unit length, isn't it? Let us say across this unit length, potential is some 5 volts, or let us say some 10 volts. How much is the potential? 10 volts. Now, what if I have to measure 0.1 volt? Will I be able to find out the balancing length here? Isn't it? I have to move jockey somewhere here, somewhere here. Even then, what I will get? Something around 1 volt difference maximum, isn't it? But what I am supposed to measure? 0.1 volts of potential difference I have to measure with the help of potentiometer. But will I be able to identify the point here? Because I cannot find sufficient length of the wire so that jockey can be tapped there and I can see 0.1 volts in the potentiometer, isn't it? So here potential per unit length is very large. Potential across this unit length is how much it was taken here, 10 volts. If I have to measure 0.1 volts, I have to move jockey very close to this A, and I may not be able to find out significant length, something that I can read from the scale, something that I can use and I can find out 0.1 volts. That's a bit difficult. So now this kind of a potentiometer is not very sensible. I mean, it is not measuring 0.1 volts kind of a small values of potential differences. It is not responding. It means its sensibility is less. Now what you have to do to increase the sensibility, to increase the sensitivity of the potentiometer? What you can do is you have to decrease the potential per unit length. Let us say potential per unit length, now it is 1 volt. Now it is 1 volt. If this is the situation, if you tap the jockey here, you will be able to measure 0.1 volts. See, approximately this length is 1/10 of this 1 volt, isn't it? So now I will be able to identify the balancing length. So from this we can conclude that sensitivity of potentiometer, sensitivity of potentiometer is inversely proportional to potential gradient. Is inversely proportional to potential gradient. It means lesser the potential gradient, more sensibility it will have. The reason is this one, whatever explanation I have given. Okay, so what about this potential gradient? How do you express potential gradient? It is expressed as I into R by L, or E by R plus Rs plus R into R by L. So this potential gradient is dependent on something like this, these parameters. Okay, so if you wanted to decrease the potential gradient, you can tune these parameters and you can decrease the potential gradient. What you can do is you can increase the resistance in the denominator. If resistance value in the denominator, how for a given cell, if Rs, so series resistance is more value of series resistance is connected, then what happens? This denominator value will be large. If the denominator value is large, X will be small. If X is small, sensitivity of potentiometer will be large. Okay, so that's what about sensitivity of the potentiometer. So with this I will conclude, students. Thank you.